Okay, good afternoon, ladies and gentlemen. Welcome to this IAS groundbreaking science lecture. This is the fifth one in the series. We try to do one per month. The next one is on Thursday. It's on chemistry, okay, by the chair of the School of Physical and Mathematical Sciences. But today we have a rising star from physics, Professor Sum Tze-Chien. Tze-Chien was a young man doing his undergraduate as well as his graduate degree from NUS. I think when he received his undergraduate degree, I was Dean of Science in NUS at that time, long time ago, when he was a young man. He was doing his PhD in Frank Watt's lab. Frank Watt was running a proton beam, a linear kind of like an accelerator, you know. Doing X-ray lithography. I remember the work that they did, you know, to show that aluminum is not the cause of Alzheimer's, right, at that time. And they were also looking at pollutants in the air in Singapore. So those were two very interesting pieces of work that came out from the lab. So Tze-Chien was a PhD student there, and then after he got his PhD, I started up this school and he applied, right? So I think we have to thank Alfred Huan as well, you know, for spotting this young talent at that young age, you know, in 2005. So he joined SPMS as a lecturer and then later became assistant professor. And then 8 years later or 6 years later, he became an associate professor. And then last year, he was promoted to a full professor. Now, Tze-Chien is one of the rising stars. He is like the new generation of faculty member in NTU. Okay, in my time, it was not like that. In my time, when I first joined National University of Singapore, I had just completed my postdoc, and there were very few people who joined the university with a postdoctoral experience at that time, you know. And then life was a lot easier. And then the head of the department would tell me, all you need to do is publish one paper a year. That's enough. And then if you, in your lectures, all you need to do is to be half a lecture ahead of the class. Not just one full lecture, just half a lecture will do, you know. Because those days we were using transparencies, right? Today you have PowerPoint and you make sure that your whole course has been prepared, right? And uploaded before you start your course. So time has changed a lot, you know, in Singapore in the last maybe about 20, 30 years. It's a totally new ball game. So at that time, the two universities were not research intensive universities, but today they are. So if I had followed the advice of my head of department at that time, I think I would have been out of a job, you know, I would not have got my tenure. So it's very dangerous, you know, what your head advises you. You have to watch the environment. The environment changed extremely rapidly, and it's still changing. So anyway, Tze-Chien is named as a highly cited researcher in 2018 by Web of Science. So I did a Google Scholar search, you know, I could have done Web of Science as well. And his most cited paper had 3,800 citations. I think that's the most highly cited publication probably in Singapore. And then if you, but unfortunately, there are how many authors there? 7, I think, you know. Nobel Prize can only be awarded to no more than 3. So next time when you do research, better count the number of participants. Okay?
Point taken.
So last year's Nobel Prize, for example, was awarded for work where citations were of about 4,000. So it's very close to Nobel Prize quality. All right? So he's a highly cited researcher, and then he has received many distinguished awards, including the National Research Foundation Investigatorship in 2018. I think you were in the first batch, I think. No. Second batch?
Third or...
Third batch already?
Yeah.
Okay, I've lost track.
Sorry, fourth batch.
Yeah.
Antoine is the third batch.
And then he has been awarded the Chemical Society of Japan Distinguished Lectureship Award in 2015, Nanyang Award for Research Excellence Team Award in 2014, and the Institute of Physics Singapore World Scientific Medal and Prize 2014. I'm sure he'll win many more awards if you keep doing good research like that. Okay? So he's currently also the Associate Chair for Research in SPMS. But he is also an outstanding teacher. He has won many teaching awards at NUS as well as at NTU. So today, Tze-Chien will share with us this interesting topic called Disruptive Perovskite.
Thank you, Prof. Thank you, Prof. Lee, for the introduction, and thank you, Prof. Lee, for inviting me here to give a talk on my research. Now, none of this would have happened if Prof. Lee had not hired me back in 2006. If he didn't give me a job as a lecturer in 2006, I will not be standing here today. So SPMS has always been Prof. Lee's baby. Okay? Prof. Lee laid the very crucial foundations, okay? And I'm very proud and very happy to be able to be part of the family, okay, and watch how SPMS grow from strength to strength, okay, over these years within the organization itself. So I got my PhD from NUS, okay, as Prof. Lee has said, and I think I'm quite fortunate that I meet a lot of very nice mentors, people like Prof. Lee, etc., that guided me along the way and pointed the direction for me to go. And more importantly, there are a lot of good students, okay, very talented students, very talented postdocs, research staff that we interacted. And it's through their hard work, their sacrifices that, okay, we managed to build up a group, okay, of what we have today. Okay, so how I actually ended up in this area, this field of ultrafast spectroscopy was because of a challenge, okay, by Alfred. Okay, so there wasn't much of a choice, simply because I need a job and I need to put food on the table for my family. So there wasn't much, but I must thank him. He has been very nice, very patient, guiding me, showing me the ropes, how to be about grantsmanship, about administration, about management, etc. But I must also say that there are ups and downs. As a lecturer back in 2005, there were also quite a bit of stigma attached, especially one who got a PhD from NUS. So in those days, it's not like today. Okay, you have NUS and NTU, being the top institutions in the world. But being someone who graduated with a PhD degree from NUS, I faced a fair amount of very, very depressing comments, but I did not let those things bother me. In fact, it was actually a great source of motivation for me to work even harder, to try and learn as much as possible. And it is a constant reminder to myself not to forget the roots where I come from and be empathetic to people, okay, have empathy for people. And humility is actually a virtue. It's not a sign of weakness, it's actually a strength. Okay, so let me just honor the real heroes, okay, of the group who actually taught behind the scenes. These are the unspoken heroes, okay, especially the FYP students, okay, in the beginning of years. As a lecturer, I'm not allowed to apply for any research grants. So the manpower that came to help me build up the lab and the group actually comes from this very talented group of FYP students. And over the years, okay, the various PhD students and also the postdocs that come and join. So these are the unsung heroes and heroines of the research which I'm going to present to you today. Now together, we learn from one another, we taught, we work hard, and we built up a group that we can make NTU proud. Okay, so a bit about my research. So what I do now is I work on the photophysics of emergent systems. I try to answer three questions. Okay, the first question is, where did the charge or where did the energy go? The second question is, what is the underlying photophysics of the system. And the third question encompasses, what can I use this knowledge for to try to make better materials, to make better devices? Now, these three questions become the guiding principles for us to tackle any research problem. And today, we have a very active program in dealing with various aspects of halide perovskites, ranging from novel photophysics, okay, trying to play doctor, okay, to some of our colleagues here to understand what went wrong with a certain solar cell and or LED, okay, what's wrong with the fundamental material, perovskite lasing, perovskite spin properties, slow hot carrier cooling phenomena, multi-exciton generation, and even nonlinear properties. So the outline of today's talk, I want to share with you a very brief history on the rise of halide perovskites. Then I will move on to the novel photophysics of the systems, highlighting the key works, okay, that enabled us to place NTU on the world map of halide perovskite research. And then I will talk about a phenomenon, okay, on slow hot carrier cooling, something that we have been chasing for the past couple of years. Okay, hopefully, by the end of the talk, I am able to convince you that halide perovskites is indeed a very interesting system to pursue this slow hot carrier cooling phenomena for hot carrier solar cells as well as for MEG solar cells. Then lastly, I will give an overview summary and talk about the outlook. Now, what we have here is the unit cell, or you want to call it the Lego block, the basic Lego block of halide perovskites. It's a very large family of materials. Now, with this Lego block, you go on to create different types of structures, ranging from the 3D, the 2D, 1D, and even the 0D structures. Now, the 3D by far is the most common that's used in the solar cells, but emerging more and more mixed dimension 2D/3D systems are coming out because of the better stability and protection afforded by the layered structures. So it gives you better stability against the ambient conditions. Now, just a bit on the Perovskite namesake. Now, perovskite refers to a calcium titanate. Okay, it was discovered in 1839. It was named after the mineralogist Lev Perovsky. Then the crystal structure was first discussed in 1926 by Goldsmith. In 1945, with the advent of the XRD, they start imaging the X-ray structure, okay, of barium titanate. Now, that's as much as this type of inorganic, this kind of perovskites go, okay, in terms of what I'm going to talk today. On halide perovskites, let me narrow down to the family of halide perovskites. Now, let's start with some prehistoric sort of history. Okay, now, the earliest paper is that by Wells, okay, in 1893, okay, on cesium and potassium, okay, lead halides. And in 1958, you image the crystal structure, you measure the photoconductivity, you get a Nature paper. Easy, right? Now, sorry, times have changed, like Prof Lee says. Okay, so times have changed. Now, this probably can't go even to APL nowadays with that. Okay, now, back to the history. Now, let me fast forward a few more years to 1990s. Now, in the 1990s, before semiconductor nanoscience become very fashionable. Now, this family of materials is actually the system for researchers to study exciton confinement effects. Now, why? The main reason is because there's very little inhomogeneous broadening from the sample properties. So it's very good for looking at quantum confinement effects. So there are these early works in the literature where the 3D perovskite, okay, that what we use in our solar cells today, is actually used as a benchmark to look at the other confinement effects as you shrink the dimensionality down to layered, to 2D, okay, to 0D, 1D, etc. And the band structure was also calculated. Now, the interesting thing is that the band gap comes about because of the anti-bonding states arising from the mixing of the lead and the iodide systems. And this gives you, this is a consequence of the strong spin-orbit coupling, and it gives you very interesting properties, which I will talk more about in terms of the defect tolerance, okay, of this particular system. Now, but, perovskite was in the wrong place at the wrong time. That part of the time, around this time, the inorganic semiconductor nanostructures were making much headway. And soon, okay, it faced its first setback because it clashed with your the inorganic semiconductor nanoscience. And obviously, you know who won. And so, this was quietly forgotten, okay? So, this is the first very sad setback that happened for your halide perovskites. Now, around the time also, people were also exploring the optoelectronic properties, okay, of this halide perovskites, mainly in the 2D layered material systems. And this are the work of, in IBM, okay, David Mitzi and company. And they were mainly looking at thin film transistors, light emitting devices, etc., okay, trying to make them to emit light. But again, I would say perovskite was at the wrong place at the wrong time. And around this part of the history, organic semiconductors start emerging. And they were making much better headway in organic semiconductors, and soon people forgot about this system. So this was sort of overshadowed by it. So it suffered two major setbacks, okay, in terms of its brief history. Now, he had to wait for his time to come, okay, and the time came, okay, around 2009. Now, this year actually marks the 10-year anniversary, okay, of the invention of the perovskite solar cell. Now, the perovskite solar cell sort of splintered off from the dye-sensitized solar cells. Now, Miyasaka was the first one, okay, who actually used this perovskite as a sensitizer in the dye-sensitized cell in a liquid electrolyte system. Now, obviously, the perovskite doesn't like liquid very much. Now, it's not very stable, but he still managed to get an efficiency about 3.8% efficiency. Now, this year is a 10-year anniversary. So in a matter of 10 years, okay, we have the efficiency has increased to about 24.2%. Now, this remarkable increase in 10 years, okay, is what silicon will take about 50 years to achieve, this kind of achievement. So, and this is a very amazing feat for a solution process system. Now, Professor Nam-Yu Park, okay, picked it up and worked on this, but he was still based on the liquid electrolyte. He still managed to improve the efficiency to about 6.5%, but still is still plagued by a lot of stability issues. Now, Canazadis then used this cesium lead iodide system, okay, as a whole conductor, okay, and it's still in the premise, under the premise of dye-sensitized solar cell, making an all-solid-state solar cell. Now, the first breakthrough came from Gratzel, okay, and Nam-Yu Park's work, okay, published in scientific reports, where they made an all-solid-state perovskite cell, okay, where the perovskite is actually used as the absorber itself, and it got about 9.7% efficiency. Now, Henry Sneyd and the Miyasaka, okay, they joined forces, and then they came out with a paper around the same time on meso superstructured nanostructures. That gives about 10.7% efficiency, okay, 10.9% efficiency, sorry. So this gives you a trace of, this 2012 marks the start of a perovskite race, okay, in terms of chasing efficiencies. Okay, a worldwide craze started where more people jump in, okay, starting to make different types of perovskite solar cells, okay, expanding the field greatly. Now today, okay, we are talking about 24.2%, okay, that's certified efficiencies by the KRICT and MIT groups. So, and this is from the NREL chart, okay, I just downloaded it, okay, 11 May, so that is the efficiency of 24.2% certified efficiencies, okay, for perovskite cells itself. Okay, now, what is the draw? Why is perovskite attracting so much attention? Okay, what is the draw? What's the advantage that it has? If you look at the processing steps, everything is very simple chemistry, low temperature, solution processable, easily manageable by high school chemistry. And what Canazadis actually term it is actually a poor man's high efficiency semiconductor. So it's easily reproducible in many laboratories, okay, and you can get a fairly decent performance, okay, in in the laboratory. So this also accounted for a rapid expansion, okay, of this system that is being investigated worldwide, and also the large growth in the field itself. Now, apart from that, perovskite seemed to hit it right. Now, it has a very suitable band gap, okay, in the range that is most useful. Now, it has very strong absorption, okay, stronger than your gallium arsenide and your silicon. And it has very good defect tolerance, okay, because of the nature of the band structure, okay. The states were formed by your antibonding states, the top of the valence band, the bottom of the conduction band. Now, this resulted in defects. They are the very shallow defects that are formed. Now, these shallow defects then, because they're easily filled, so they are termed as very benign. Now, in contrast to typical systems where you have deep defects, now that would cause you a lot of problems, okay, in terms of purifying the material. So that's why it is a very special combination of traits that gives perovskite this very unusual property. Okay, so solution process works. Of course, we now know more about this now. And the last property I'll just say is it has a very small effective masses for both the electron and hole. As a result, your mobility is actually pretty good, okay, in this meteoric system. And it has started to encroach into nanoscience. Now, using wet chemistry, you can easily play with the chemistry and then start to confine, restrict the growth in various dimensions. You get your nanoplates, your nanorods, your quantum dots, your core shell structures, your layered structures, etc. Now, this opens up a whole new playground for many people to actually start studying the novel properties of this very interesting system itself. Now, so Carat perovskites are pervasive, okay, and very disruptive. Now, it certainly has disrupted my life. But if you look at this little crystal here, it really looks like a strepsil sweet. And that's a single crystal. So highly dangerous. Don't leave it lying around if you have small kids. Okay, now something that is probably impending in terms of disruption, okay, the perovskite silicon tandem cells. And the idea then is to stack they're using the perovskite as a front face to collect the blue wavelengths, while your silicon collects the rest of the other wavelengths. So combining this, it has already attracted a fair amount of commercial interest, and the record efficiency by Snate's company, I think it's 28% efficiency. So this is something that we can look forward to, and possibly something that will be coming, disrupting the usual photovoltaics that what we see, okay, in the market. Okay, now, the last slide that I will talk about this little brief history. Now, it has expanded its tentacles to various different fields. Okay, it has greater impact in terms of perovskite lasing. Now, lasing is something that we started the field here. Okay, and it has spread from Singapore to quite over the world. Perovskite LEDs, perovskite detectors, okay, perovskite memories, and even transistors. That's Chesary's nice picture. Okay, the light-emitting transistors. Okay, so it has great impact just beyond just the usual photovoltaics, expanding into various aspects of the optoelectronics. Okay, now that is, in a nutshell, a very brief history, okay, of the milestones that are achieved in perovskite. Now, I'll just gear the talk towards the novel photophysics of this system. Now, the methyl-ammonium lead iodide system now is fairly well understood. But if you trace the history, okay, you can trace a similar milestones. Back in 2013, 2012, 2013, there wasn't much work done on the photophysics. And in fact, our work was one of the first few work papers, okay, trying to make sense of what is happening in this very interesting material system. So you can trace the history, okay, the milestones similar to that of that. There isn't much space to include everything, so I just included a few, okay, focusing more on the hot carrier phenomenon, okay, or what we are going to talk about, or what I'm going to talk about later on. Now, this is the work, okay, those are the two gentlemen, okay, Sui Xian is somewhere in the audience, okay, Gui Chuan now is in Macau, okay, University of Macau, probably getting his tenure this year, okay, so he should be getting his tenure this year. Okay, so the discovery of very long-range balanced electron-hole diffusion lengths, okay, in this system was a bit of a surprise, given that this is actually a solution process material. Now let's go back to that part of the timeline, okay, in around 2012, 2013, where the field started exploding. Because people start jumping in after Henry Snade's paper, after Gretzer's and Nami Park's paper. Now, perovskite was, many groups were working on trying to improve the efficiencies, and were trying many things. Now, there were reports that come out that perovskite works as an absorber layer. There are also reports that come out that show that perovskite works well as an absorber and an electron transporter. Okay? And there are also reports that come out that perovskite works as an absorber as well as a hole transporter layer. Now, all this, we piece the puzzle together, and we came to dawn to us that this material may have very interesting ambipolar charge transport properties. By that time, it wasn't so obvious. Now, people were just testing out the versatility and then reporting the efficiencies. No, hey, I got this and I got that. So we came up with an experiment to try to understand this photophysics. Now, this was some typical experiments that usually we do in our group. So we try to decouple the electron and hole transport lengths by interfacing, okay, either an electron extraction layer or a hole extraction layer, okay, on the perovskite layer itself. Now, so the perovskite layer is about 65 nanometers thick. So this is a bi-layer configuration. Now, and after you interface them, you look at the photoluminescence. Now, the photoluminescence suffer a big hit, okay, after you interface it with your electron or hole extraction layers. Similarly, the lifetimes actually decrease, and this amount of photoluminescence quenching is actually very significant, okay, and it's comparable to the bulk heterojunction donor-acceptor pairs that we usually work with. For example, the P3HT PCBM systems, where the donor and acceptor domains are only about 10 nanometers apart from one another. Now, in this case, we have a bi-layer configuration where we have layers about 65 nanometers. Now, what all this tells us that it suggests that the diffusion lengths are actually fairly long. Now, how long is long? So we turn to a very simple diffusion model. Okay, put in very conservative estimates to try and get a lower estimate, okay, of the diffusion length. And it turns out, okay, that the diffusion lengths, after we fit soft equations, the diffusion lengths are fairly long, okay, around hundreds of nanometers. Now, we thought it was a mistake because given a solution process material system, solution process materials typically give you only diffusion lengths about 10 nanometers. And this is already an order of magnitude longer than any typical diffusion solution process material. Now, we were a bit skeptical, thinking that, hey, this is a PL experiment. We may just be looking at the emissive species. Now, let's try another approach. Okay, let's go to pump probe spectroscopy. Okay, pump probe or transient absorption spectroscopy, okay, does not just monitor the emissive species, it also monitors the non-radiative species as well. So we do a selective excitation, okay, a selective pump, a selective probe of the levels, okay, measure the lifetimes, okay, from the recombination, and indeed, okay, it validates the PL experiments, and the lifetimes, the diffusion lengths are indeed long, of the order of hundreds of nanometers. And having a material that has a relatively balanced electron and hole diffusion lengths, now that is pretty peculiar, especially a solution process material. You usually don't see this kind of materials. So this is actually the key finding that's reported in that paper. Then that's the reason why your solar cell works so well in different types of configuration. Okay, and it has a far bigger impact. It not only works well in solar cells, but it also in general for optoelectronics, as what we have seen how the field has expanded, okay, these days. Now, a second key finding, which is actually the basis of my remainder of my talk, was this secondary discovery. Okay, any paper you can only have one main point and possibly a smaller point. Now, this is the smaller point, where we found that there's actually very interesting slow hot cold cooling process occurring in these valence bands. Now, we see that from the interacting dynamics that we see, okay, from the depletion of one level, which is shown by the decay of the signal, the black signal, and the rise of another signal when we are monitoring, okay, a higher valence band level. So you can imagine this level is actually losing your carriers as the whole is basically behaving like a bubble and is floating up to the next level. So that level is emptying out while the upper level is slowly filling up with more holes. So that cooling process is fairly slow, around 0.4 picoseconds. Now I will elaborate more on this discovery, and this is the basis of our subsequent number of years of work tracing this phenomenon of slow carrier cooling. Okay, I'll come back to that later. Now, so in the gist, in summary, okay, the significance of the finding is that the diffusion lengths are very long, and that's the basis that the charges can actually be extracted, okay, before they can be before they recombine in the solar cell. And this has far-reaching implications. As I've said, okay, it has expanded beyond just your solar cells. Okay, it has implications for light-emitting your light-emitting devices, okay, your photodetectors, etc. So in general, for optoelectronics. Now, a second discovery was a second piece of work that actually the work was done at the same time, but simply because we don't have the bandwidth to write 2 papers at one go. Now, for the science papers, Sui-Xian can remember, we were working day and night, camping basically in my office, writing that manuscript. We finished, by the time we finished submitting, I think it was about 4 a.m. in the morning. We went to McDonald's at Pioneer Mall, which is 24-hour McDonald's, and we had our breakfast. Okay, that is still very vivid. So the same thing happened for this paper. We were also drafting and writing day and night in the office, barricading ourselves. Now, the discovery was made almost at the same time because lasing is something that we always do in the group. And I remember Kui Chuan coming to me very excitedly. It lasers, it lasers. Okay, so we know we hit something, we probably struck something very exciting, okay? Because as a solar cell material, you would not expect it to be a good optical gain medium. So this, together with the long balanced electron hole diffusion lengths, we quickly filed a patent, okay, to protect the idea, because if you can make a solution process optical gain medium that's electrically pumped, that would be a game changer, okay, for the field of lasing. Okay, so that has been patented now. Okay, so the finding here is we find that the threshold is fairly low, okay? It's very easy, you hit it very easily, you get amplified spontaneous emission. Now, and the significance is that given that as a solution process material, you can easily mix and match the precursors, and then you can tune a broad emission length, a broad emission range, okay, ranging from 400 to 800 nanometers. Okay, that was demonstrated in this paper. We eventually extended the range to around 950 nanometers using tin-based perovskites. That means you go into the infrared. So in principle, you can tune your optical gain media, okay, any wavelengths within this range, okay, from visible all the way to infrared, okay, using this this perovskite system. Okay, now that is in a nutshell of the 2 papers which help place NTU in the world map of perovskite research. Now, I'm going to spend the next couple of minutes to talk about something that, the secondary discovery that we have been chasing for the past, I think 6 years, okay, on slow hot carrier cooling phenomenon. Now, before I do that, let me just do a quick motivation, okay, of what's this, why do this research? Introducing you to some of the concepts of hot carrier cooling, okay, multi-exciton generation, etc., as a novel approaches to try to enhance the efficiency of solar cells. Now, in any solar cell, okay, any single junction solar cell, one of the biggest energy loss comes from what is known as your thermalization loss. Now, this is also your carrier losses, okay, your hot carrier losses. Now, how does this thermalization of hot carrier losses comes about? Now, look at the semiconductor material. Okay, if the semiconductor absorbs a photon that has an energy larger than the band gap, now it creates an electron and hole pair high above the band gap. Now, this electron and hole pairs has a lot of energy. They are termed as hot carriers. Now, these hot carriers will lose their excess energy very quickly to the lattice, to the phonons. Okay, in a very short period of time, typically around 100 femtoseconds. Now, if you can harvest this energy before it loses to heat, you have a way of increasing the efficiency of the solar cell. So that is the motivation behind this idea of having this, trying to harvest these hot carriers. Now, there are two concepts where you can try and do this. One is to extract the hot carriers directly, okay, in what is known as the hot carrier extraction. That gives you about theoretical efficiency about 66%. Now that allows you to enhance the photovoltaic. Now a second concept is based on multiple exciton generation. Okay, that is based on enhancing your photocurrent, and that increases your efficiency to about 44%, theoretical maximum. Now, both these approaches share one common key criteria. You need the hot carrier cooling to be slow in order to make these two processes more favorable for you to extract, also more favorable for the multiple exciton generation to occur. Okay? Now, what is hot carrier extraction then? Okay, let me just illustrate this with a cartoon. The idea is you want to have selective electron or selective hole contacts. Okay, after excitation, before the hot carrier have a chance to relax, you want to extract it before you do. And definitely having your hot carrier cooling to be slow makes things a little bit easier. Okay, so that's the first concept. Now the second concept involves the absorption of a high energy pair of photon. So in this case, I illustrate this with 3 times the band gap energy. Now this hot electron and hole pair then goes on to, this electron and hole pair then goes on to create another 2 pairs of electron and holes through what is known as impact ionization or the inverse OJ process. Now again, your slow hot carrier cooling does matter. It gives you, makes this process more favorable. So in this case, we have 1 photon, you get 3 electron hole pairs being produced. Hence the term multiple exciton generation. Now, what's the problem with traditional semiconductors? Now, in typical semiconductors, you have in the bands are closely spaced, especially for bulk semiconductors. You have very rapid relaxation of your hot carriers, now typically in the order of hundreds of femtoseconds. And just for comparison, okay, for the halide perovskite films, which I shown earlier, okay, it's a bit slower, around 400 femtoseconds. So in the literature for your semiconductor bulk traditional inorganic semiconductors, now people in the field have tried to go nano. You shrink your shrink it down to nanoparticles, shrink your bulk semiconductor down. As you shrink, your band structure starts to recede and your levels start to become more discrete. So the idea is, if you go to a nanoparticle or nanocrystal, you have very discrete levels that's reasonably far apart, and for a carrier to relax from one higher level to the lower level, you need multiple pairs of phonons in order for this transition to take place. Now, having more phonons means that the process is actually getting more improbable. Hence, the term, the phonon bottleneck, is there. So that's the meaning of phonon bottleneck. Now, it turns out that the phonon bottleneck, as you shrink down, okay, for this traditional colloidal nanocrystals like cat sulfide or cat selenide, the phonon bottleneck is breached. Now, due to various reasons, okay, due to surface defects, due to Auger effects. So again, it wasn't very successful, this concept for phonon bottleneck using the phonon bottleneck to slow down the carrier cooling in traditional inorganic nanocrystals. Now I'm going to talk about halide perovskites. Now this is a combination of the various works that we have been studying, okay, this phenomenon over the years. Beginning with the science work, okay, the discovery of 0.4 picosecond hot hole cooling. So the question that we asked, okay, are perovskite hot carrier solar cells feasible? Now it's a very enticing concept because you can increase the theoretical efficiency up to 66%. Now our motivation is to look at whether the science is there for this concept to be even feasible in the first place. Okay, so just a reminder, okay, in this case, you excite, okay, with selective electron contacts. You want to extract the hot electron and hot holes before it has a chance to relax to the band edge. Now, just a recap, the first evidence, okay, comes from this interacting levels that we see, okay, the 0.4 picosecond hot hole cooling, where we see a depletion of one level followed by a simultaneous rise, okay, in the signal, the filling of a second level. Now, we see a slow hot hole cooling process of 0.4 picoseconds, but that is actually still too fast for any practical device to make any practical device out of it. Now, we continue, we did not lose focus with this idea. We continue over the years, okay, from 2013, we were making sense of the band structure, trying to clarify and understand the structure. We kept this information of slow hot hole cooling at the back of our minds. We KIV the idea. Now, it becomes clearer to us, okay, that we are not only seeing a dual valence band, but we are also seeing a dual conduction band, okay, in this perovskite system. And this dual valence and dual conduction band coincidentally has an intraband spacing around 1 eV. And in this work, we reported that, okay, we clarified that there's not only slow hot hole cooling, but the electron cooling process is also slow. Now, immediately it changes the whole game, because having only the hole that is slow is not going to help if your electron is not slow enough. And having an electron and hole that is not cooling at the same rate, that will give you a lot of problem. And again, the magical thing about the very small effective mass, very small similar effective mass of perovskite comes into play. Okay, so it came with a very nice coincidence here. Now, so having a balanced hot electron and hot hole cooling, it definitely makes it really more feasible. It looks more likely that you can actually attempt to try and make a device out with this concept. So we may have stumbled, we have therefore stumbled upon a very interesting system that we can potentially use. Okay, so let me, we then, the next stage then, we took the path, we got inspiration from the colloidal nanocrystals, the semiconductor inorganic colloidal nanocrystals. We went nano. We went to nanoparticles, perovskite nanoparticles, to make use of the quantum confinement effects to try and slow down, to enhance this phonon bottleneck. Now, as we shrink the nanoparticles down, okay, from sizes from about 12 to 5 nanometers, and we measured the cooling time, we see a slowing down of the rise time. The rise time, as I've shown earlier, tells you about the cooling, how fast the cooling is actually occurring. It's actually becoming slower as we shrink the size of the nanoparticles. Now, if you compare that with cadmium selenide quantum dots, which we do as a control experiment, as you shrink the particles down, your rise time goes faster. So that is a signature that what I've said, that the phonon bottleneck is breached. So you can't really make use of your phonon bottleneck, okay, in your traditional cadmium selenide quantum dots. So we have a very, very different, a very contrasting, a new class of nanoparticles which we can use to preserve and keep the bottleneck intact. And one of the key reasons why this bottleneck is absent, okay, in your perovskite, because unlike the cad selenide, you have a whole manifold because of the hybridization effects, and that gives you very closely spaced levels. So if you think about it, if you lose either the hot electron or the hot hole, then the whole concept fails. Your bottleneck is gone, but whatever bottleneck effect that you are trying to preserve. Okay, now the quantum dots, a little bit of the quantum dots. Okay, these were prepared by Subodh's group, okay, in Repan and Subodh's group. So they make the methyl-ammonium lead bromide nanocrystals. So as you shrink the nanoparticles, okay, from large to small, you have a shift of your blue shift, okay, of your band gap. Now, we perform your pump and probe spectroscopy, okay, on this system, monitoring the band edge photo bleaching and the hot carrier, the high energy tail here. Now, these are nanocrystals. We are comparing between nanocrystals and bulk films. We excite at low pump fluence, high pump fluence, low pump fluence, and high pump fluence for the nanocrystals and the bulk films. Okay, so what I want you to draw your attention is the high energy tail here, which tells us about the hot carrier cooling phenomena. So if you look at the high energy tail in your nanocrystals at low pump, this tail is much, much more pronounced compared to perovskite bulk films. So we have a fairly interesting phenomenon there. Now, this high energy tail, you can fit a Maxwell-Boltzmann distribution, okay, and try to determine what is the carrier temperature. So this is what we did, okay, and we plotted this carrier temperature as a function of your lifetimes. So what we found from this, as you go to nano structure, okay, you get about 4 times hotter hot carrier temperatures, okay, and your lifetimes can increase as long as almost 2 orders longer, okay, for hot carrier lifetimes. Now, this is a very significant lengthening, because with this kind of lengthening, you can get thicker layers and you can make a practical device out. So that is the basic understanding behind this. Now, I will very quickly talk about the mechanism, because the mechanism was also changed. We have a separate team, which I'll show in the next couple of slides, on a more detailed study on this. So in this case, there are 2 mechanisms at work. One is the hot phonon bottleneck effect, which dominates at low carrier densities. Now, at higher carrier densities, you have an OJ reheating process. Okay, I'll talk more about these mechanisms in the next couple of slides. Now, but what I want to draw your attention is, given the lifetimes that we measured, now the diffusion lengths, we made an estimate of the diffusion lengths, okay, for this hot carrier lifetimes. Now, that gives you about 16 to 19 nanometers. Now, this is a fairly thick film. Okay, it's still possible to make a device, okay, with this kind of thicknesses. Now, if you compare for bulk films where the lifetimes were only about 0.4 picoseconds, now that restricts you to something like less than 10 nanometers, and it's very challenging to actually even try to attempt to make a device with something that's only a 10 nanometer layer. Now, I'm going to move on to talk about hot carrier extraction. Yes, we managed to slow down your carrier cooling by going nano. But if you cannot extract the carriers, it's still just a thought experiment, okay? Nothing's going to work. So this part of the work, we try to extract these hot carriers out. Now, the original quantum dots has very long chain ligands, the olealamine. We have to do a ligand exchange, okay, to exchange them to shorter ligands, okay, the ethinyl EDT. Then we spin coat them, okay, on a substrate, and we interface this perovskite nanoparticle layer, okay, nanocrystal layer, with an electron extractor, okay, a BFN, okay, organic semiconductor. Okay, now this was determined to actually align well above, okay, your conduction band, okay, well above your conduction band. So we performed the experiment of pump and probe, okay, monitoring the photo bleaching peak and also the high energy tail here. Okay, now, with the presence of the BFN, okay, those are the solid lines, your high energy tail disappears, okay, compared to without the BFN. And monitoring, using the peak intensity here, the peak value here, as a peak photo bleaching signal, as a benchmark, okay, of what is the efficiency of the hot carrier extraction. Okay, we find that the signal reduces by about 83%, okay, as some sort of a measure of the hot carrier extraction efficiency. Now, the carrier temperatures actually decrease, okay, with the presence of this BFN extraction layer. And we perform the experiment one step further. We perform an infrared probe of the BFN, and we do monitor that there are charges being injected, okay, into the BFN layer. Okay, that's seen from the spectroscopy that you get a photo-induced absorption signal, okay, in the infrared. Now that gives us very clear confidence that the charges has indeed, okay, gone into the BFN. Now, we went one step further to look at the influence of excess energy and also the thickness of the film. So we pump it with more energy, okay. The main message, the take-home message here is, if you have your carrier temperatures hotter, okay, higher extraction, okay, hotter the temperature, okay, the more efficient is your extraction efficiency. Now, the thinner the film, the more efficient is the extraction. Now, that's obvious. But for 16 nanometer thick film, okay, you still get something of efficiency about 60% extraction efficiency. Now, all this points to the suitability for use in a concept known as extremely thin absorber sort of solar cells, or you can use it for concentrated solar cells when you can make use of very intense radiation to try and reheat, okay, making use of the OJ recombination, okay, the OJ effects, the OJ heating to keep the temperatures hot, okay, in your carriers. Now, a second team, okay, led by Jian Hui, okay, a very talented PhD student, okay, went on to study this hot carrier cooling mechanisms. Okay, he together with Dr. Xu Qiang, okay, who is a DFT scientist, okay, tried to make sense of try to get some more insights into the cooling mechanisms. Now they came out with a model that tracks the phonon, the rate of population increase of phonons from your LO phonon emission and LO phonon absorption, and then we tested the model as a function of hot carrier temperatures, as a function of temperature, as a function of pump fluence. And from our experimental data, the model is able to explain all this data fairly well. And what we have here is a plot of the energy loss, okay, taking care of the electron-phonon coupling, taking care of the OJ heating process, and that gives you a fairly good fit, okay, over these various delay times. Now, the main finding is that around 10 to the power 18, okay, your pump flows up to about 10 to the power 18 centimeter minus 3, the hot phonon effect dominates. Now, more than 10 to the power 19, you have an OJ heating effect that comes into play, okay, and that gives you your, that is the mechanism that drives the hot carrier cooling, okay, in the halide perovskites. Now, from DFT, okay, performed by Xu Qiang, okay, the phononic band structure, okay, the phonon band structure, the yellow zones tell us the L phonon levels, okay, and the green zone tells us the acoustic phonon modes, okay. There is a clear mismatch, okay, between your L phonons and 2 times the LA phonons. Now, this suggests to us that the Clemens process, okay, where an L phonon decays into the 2 phonons, 2 acoustic phonons. This mode of relaxation is actually suppressed, and that's the main reason why we think that the phonon band, the hot phonon bottleneck is still intact, okay, in this halide perovskites. Now, the remaining time, I will talk about the last concept, okay, that is on the multi-exciton generation solar cells. Again, we ask the same question, okay, is MEG solar cells feasible? So we now have greater confidence. We know that the hot carrier cooling process is actually fairly slow. Okay, so we went on to test this concept, whether we can get MEG effects in this system. So in the case of MEG, you have one high energy photon creating multiple pairs of electron and holes, okay, from impact ionization, or what is known as your inverse OJ effects. Now, the MEG, a little bit of history to that. Now, this was first observed in lead sulfide, lead selenide quantum dots. Now, this was the work of Klimov and Skeller. Now, but the main limitation in this type of nanoparticles, okay, is that the MEG threshold is very high. It's around 3 EG. Now, you want to have a lower threshold because it helps with increasing your efficiency. Ideally, you want to be as close as 2 as possible, because you only need twice the amount of energy to get 2, okay? So you want to be as low as possible. Now, the dots that we use are the formaldehyde lead iodide dots, okay? We changed this dot system to go to a radial wavelength, okay, around 750 nanometers. This was made by Raihana, okay, from Subodh's group, okay? And these dots have, are in the intermediate confinement regime, okay, weak to intermediate confinement regime. So we made different sizes, okay, from 30 nanometers down to about 7.5 nanometers. Now, from the transient absorption, okay, we make use of transient absorption to look at this evidence for the MEG, multiple exciton generation. In fact, we were looking at the signature of the bi-exciton. Now, experiments have to be done very carefully to make sure that your excitation fluence is very low. Otherwise, okay, if you have a high excitation fluence, you can still create a multiple exciton, but that's not the MEG phenomenon that we are trying to chase. Okay, what we want is, we want to perform the experiment at very low pump fluence, and we perform the excitation below the MEG threshold and above the MEG threshold. So the signature comes about from this bi-exciton signature, which is a very fast decay of the photo-bleaching signature, performed at low pump fluence, okay, very low, 0.07, okay, average electron hole pair that's inside there. Okay, so this gives you very clear evidence that your multiple exciton generation is actually occurring, okay, with a formation of this bi-exciton. Now we can go on to extract and determine what's the MEG quantum U by taking the ratio, the amplitude ratio of the bi-exciton with that of the single exciton. And in the case of the smallest dots, it gives us a quantum U about 1.3. Okay, as you make the particles go to larger particles, this MEG quantum U actually decreases. Now, a key litmus test is that of the threshold. Now, I draw your attention to the open dots here, okay? The open red dots and the black dots. Now, those are the lead sulfide and the lead selenide nanocrystals, okay? One is from data that we reproduced from the literature, okay? The other one is data that we collected using our experiment. Now, the threshold is around 3 times the band gap. Now, if you compare that with the blue dots here, now the threshold is around 2.2. EG. So we managed to actually lower this, okay, threshold significantly to only about 2 times, okay, close to 2 times with this perovskite quantum dots. Now the MEG lifetimes, we estimated it to be around 90 femtoseconds, okay, which is much faster. Okay, of course, having a slower hot carrier cooling does matter. Okay, and the last point which I want to say, okay, if you have your threshold closer to about 2 EG, you actually get much higher power conversion efficiencies. So instead of just at 3, so if you get anything closer to this 2, you're going to get a better conversion efficiencies with this this kind of systems itself. So let me end off, okay, with a quick summary. Okay, so I have shared with you, okay, a very brief history of halide perovskites. Now, perovskites are expanding to a lot of different areas, okay, a lot of different fields. Okay, it's very invasive, I would call it, okay, and potentially disruptive, especially in the case for your tandem, your perovskite silicon tandem cells. So it looks like we have to look out in the near future. Some very exciting things will be happening, especially in the photovoltaic arena. Now, I've shared with you some of the work that we have been doing, okay, for the past couple of years, chasing the phenomenon of slow hot carrier cooling, okay, and even demonstrating this MEG. In fact, that paper was actually the first report of multi-exciton generation in perovskite nanocrystals. So the science shows that the system can support these 2 concepts. Now, what is actually stopping us from trying to do to make a real device out would be the chemistry, I believe, and also the engineering, okay, in order to put these 2 together. So there are still hurdles ahead, okay. In order to make a real practical device, we need these 2 areas to actually keep up with the field, and possibly in the near future, I hope this could actually start a whole new field, okay, in hot carrier and also multi-exciton generation of solar cells. Okay, so more things are coming. Okay, David and Sui-Hsien, these 2 dynamic duo, have been chasing things in the lab. Okay, doing the pump push probe spectroscopy. Okay, expanding our understanding of this Biffen extraction, and then they found evidence of a barrier that's at the interface there. Now this is under revision, and hopefully it will come out soon. Okay, so with that, I'd like to acknowledge the people in the work, doing the work. Also the collaborators who actually provided me with a lot of the samples, and of course the funding. Without moolah, like Prof Lee always says, without moolah, nothing moves. So you need moolah, okay? And with that, I thank you for your attention, and I'll be happy to take some questions. Yes. Yeah, Annalisa. Oh, yeah, okay. Yeah.
Thank you very much for your talk. I have a number of questions. In your talk, you mainly focus on the organic, inorganic, hybrid perovskites. So I'm wondering, can you comment on the hot carrier situation for the all inorganic perovskites?
Yeah, all inorganic, I think coincidentally, okay, when our paper came out, there was a neck-to-neck paper that came out just behind us. Okay, so that is on an all inorganic. Yes, it is real. You can still see it also in all inorganic. Okay.
Can I just ask another quick question? How does the slow hot carrier cooling time affect the radiative or the decay, PL decay time?
They occur at very different time scales. Okay, the radiative decay takes place much slower compared to that slow. Though we say it's slow, slow is kind of relative. Now, it's probably even really inconsequential given the nanoseconds versus the picoseconds. There's 3 orders of magnitude difference. So there's hardly any, to answer your question, there's hardly any effect in that for the radiative decay because we are talking about very different time scales involved. Okay, for your radiative recombination, for example, it takes place in the order of 1 nanosecond or few nanoseconds. Now, what we're talking about, this slow is still of relative, it's relative, you see, in terms of that. Okay?
Okay, can I just confirm that the experiments that you did were all at room temperature?
Yes.
Okay.
So for the hot carrier cooling, yes, they were all done at room temperature.
Okay, thank you very much.
Yeah. Yes. Hi. Yeah. Annalisa. Yeah.
So thank you very much.
It's on, I think.
Can you?
Yes. I think
yeah. The back, can you? So thank you for the very nice talk. And my question is a bit more general. So what do you think, in conclusion, will be the key aspect to really get the hot carrier solar cell to work? More on the interface or how to change the material? Which will be the key aspect to work on? So it seems that you need to go small inside, but not so small, because you cannot confine too much. So which is, if you should summarize in 3 points, what should be our taking home?
I think the take-home message would be now we have done quite a bit of work in terms of the science in the basic material itself. The material can sustain slow carrier. Okay, the hot carrier cooling is slow. It's there. Okay, now improving that will only make it a bit longer or tuning it there and changing the wavelength, the band gap, for example. Now, what is key, I believe, is the interface. Okay, the interface and the suitable extractor. Okay, and possibly the architecture. Now, the architecture involved may not be, especially for your hot carrier cells, will be a little bit different from your traditional type of cells. Now, those parts, the device engineering need to catch up with that, okay, on making the suitable architecture. Because if you look at it, you not only have to harvest the hot carriers, you also do not want to lose the cold carriers as well. So you need the architecture that is able to support both and be able to extract both of them at the same time. And that, obviously, the interface then becomes a bit important aspect as well. Okay, when you have different architectures coming into place. Now that part, probably we need to do a lot more work in that, okay, in the terms of the engineering of that. Yeah. Stevie?
Okay, I just noticed that when you decrease the size of the perovskite nanoparticle, and you found that the cooling time become longer. So how about you use the typical 0D perovskite to measure the cooling time?
Sorry, can you repeat that, the last part of it? How about using the
typical 0-dimensional perovskite instead of
the 2-dimensional? You mean use the
0.
The 0D. The 0D, you will have you talk about the real 0D, okay, the structure, the 0D structure. Now you will have a bit of issue because the band gap is actually very, very wide. Then that is not so suitable for making the solar material. So yes, it's an interesting question, but because when you go to 0D, your band gap becomes very UV. So that is not so ideal for that. Yeah, so we still stick to the 3D perovskites, but we confine it. Yes. Yes.
In order to see the effect of this, so in order to see the effect of this multiple excitation generation, you told that there should be some optimum thickness of this perovskite.
No, not in the optimal thickness for the multiple exciton generation. Okay, we were tuning for the band gap, okay, because we want to be around 2 times, okay, that. So we were going to around 780, the band gap. Now, it's not so much of the thickness, but the size of your particles, okay, that what we are trying to see. So as you string down, in this case, I've shown is the intermediate size, okay, and that's where you see a high efficiency in terms of your MEG generation. Yeah.
You see inside the perovskite, are they explosive?
No, I can ask my chemist there. No, it's not. Yes, Ranjan.
Excellent overview and excellent talk, TC. So TC, I was just wondering about a question that is the future of perovskite solar cell bright?
It looks quite bright in terms of, I think Nazaruddin actually demonstrated something more than a year stability with the perovskite, large area perovskites. Okay, he managed to demonstrate more than a year stability. The concern is probably the lead, whether the lead will leach out. So that is, I think, can still be solved with the packaging. Okay, so a very standard answer people will always say, you have lead in your lead acid batteries, right? Your car batteries, and no one is complaining about it, right?
Okay. Okay. Thank you. Thank you.
No further questions. You have to go home for dinner.
Okay, thank you, thank you. Thank you, thank you, thank you,
Thank you all for coming. The
Thank
next lecture is on Thursday.